looking through one of my old number theory books, and I noticed this interesting proof about the square root of 2 being irrational, and that it was, quote, an easy proof in base 3. So I wanted to run through that with y'all. Now, let's just talk a little bit about why I guess base 3 is advantageous here. Let's see. Let's just kind of review. You know, in base 3, the allowable digits would be 0, 1, and 2. Okay, there's only 3 permissible digits in base 3, and that would be 0, 1, and 2. All right, and just, you know, it's just like base 10 where there's 10 permissible digits, 0 through 9. Now, an example of a number in base 3, we'll just do I guess a 3-digit number, 212, right? 212, we'll try that out. Now, a lot of times in context, you can just write that down. Everybody knows it's base 3, but you can put this subscript 3 here to indicate that's the base. Now, this has an expanded form, much like decimal, except we're dealing with base 3, which means 2 times 3 squared. Okay, this is again called the expanded form, plus 1 times 3. Plus just 2 times 3 to the 0. And again, I like putting that. A lot of people just put 2, but in keeping with the base, I'll call it 2 times 3 to the 0, 3 to the 0 being equal to 1. All right, so right here, I believe we get, what is that, 9 plus 3. Or excuse me, 2 times 3 squared is 2 times 9 is 18. Plus 3 is 21. I'm getting 23 in base 10. And you don't really see base 10 written this way very often, but since we are mixing bases here, let's just double check. 2, 1, 2, this means 2 times 3 squared. 3 squared is 9, 2 times 9 is 18. Okay, 1 times 3 is 3, 18 plus 3 is 21. 21 plus 2 would be 23 base 10. Okay, so that's just an example of what we mean by base 3. Now we're going to use this in kind of a cool way here. There's a lemma here that's fairly straightforward. It's a little bit of a pain because you have to allow for the possibility that the last digit could be 0. The last 2 digits could be 0. The last 3, and so on. Now, in a way, it doesn't make sense with such a small number as square root of 2. But just to be safe, we're going to go ahead and include this non-zero piece right here. So if x is a base 3 number that ends in 1, certainly x squared is equal to 1. So nothing to worry about there. Okay, but what if x ends in 2, or its last non-zero digit is 2? And this is kind of just a simplistic example right here. 2 squared. 2 squared means this is equal to 4 base 10, but that's equal to 1 times 3 plus 1, right? Expanded form, 1 times 3 plus 1. So we do have 1 times 3 plus 1 is equal to the 4 right here. And so when you square this digit, you do get 1 as the terminating digit. And notice the very same thing would happen right here. I won't write this out, but let's say this number, this example that we use right up here, if you square this out, 212 base 3, quantities, squared like that, we'll do it parenthetically here. Its last digit, because of this truth right here, just because of the nature of multiplication, you would have a 0 position underneath here when you multiplied it out. So this would have a last digit. I'll just put LD, last digit. The last digit LD equals to 1. Okay. Again, not a formal proof, but hopefully convincing. All right. Now here's an example of the last non-zero digit. Okay, so 2 would be the last non-zero digit in this example. All right, 2 would be the last non-zero digit in this example right here. Base 3 number squared. Now this base 3 number squared is equal to 15 base 10 squared. There's a way to do this out in base 3. We'll convert it to decimal. It's a little bit easier right now. But so this would be 1 times what? 9 plus 2 times 3. That definitely gives you 15. 15 squared is 225. And again, I left the work out here, but this isn't too hard to believe. We can write out, we can verify just by checking here. This expansion right here, this would be the 3 to the 4th position, the 3 cubed position, the 3 squared position, the 3 to the 1st position, and the units position. So this would be 2 times 3 to the 4th. And we could skip this part, but in case you don't trust me here, 2 times 3 to the 4th plus 2 times 3 cubed plus 1 times 3 squared. And it's a good thing for me that we had 2 zeros there. I was running out of room here. Plus 1 times 3 squared. And of course, it's plus 0 right in here because you have these positions right here being 0. So 3 to the 4th is 81, so this would be 162. This piece right here would be what? 3 cubed is 27, 2 times 27 is 54. Plus 9. And it does look like that sums to a 225 base 10, right? There you go. Okay, folks. So, but again, the key part of this is that the last non-zero digit was 1, right? Now, again, I don't represent this as a proof. I think a formal proof would be kind of a pain. You know, you do it, but I think hopefully this is convincing enough for y'all to believe me on this. And so again, we have 2 separate circumstances. If there are no terminate, if the base 3 number does not end in 0, it's very clear that a squared base 3 number has to end in 1. Okay, and if it does end in 0, hopefully this is convincing that the last non-zero digit would have to end in 1. Okay, so we're about done with the proof right now, believe it or not, because this is the way the regular square root of 2 is irrational proof starts out. Okay, you suppose that it's equal to a over b, where a over b is reduced. We're not even doing that, but in the classical proof, when you do that and you suppose that a over b is reduced, then you get this statement: 2b squared is equal to a squared when you multiply by b and then square both sides. And this says that a squared is even, which means a is even, but that ends up proving that b has to be even, which would say it wasn't reduced. And that's the proof. That's the contradiction in the classical proof. Now, this one, in some sense, is even easier because we're not, after you get this lemma out of the way, okay, we get the very same representation right here. Okay, but notice here that if this were true, then the last non-zero digit of this guy right here would have to be 2. In other words, 2b squared, b squared is a base 3 number, okay, and so that means that b squared's last non-zero digit would be 1, but 2 times that would turn it into 2 right here. You see, isn't that cool? All right. Now, in a similar fashion, and it's even easier, a squared's last non-zero digit is 1, right? That's what the lemma says right here. Let x be a base 3 number, then the last non-zero digit of x squared is 1. So you see, this is our contradiction right here. This is a contradiction because obviously they're saying here that 2b squared, this says that 2b squared has a last non-zero digit of 2, and that a squared has a last non-zero digit of 1. Well, no way, because they're equal to each other, right? They're equal to each other, this statement says, okay, from this supposition here. So we suppose that root 2 could be written as the ratio of 2 base 3 integers without them being reduced. All right, so that's the contradiction. And what is the contradiction? We're contradicting this supposition right here. So we contradict, this contradicts, it speaks against, right? Contradicts, speaks against. This contradicts our supposition that root 2 can be written as the ratio of 2 base 3 integers. Okay. And if you contradict that, that means it can't be written as a rational number, so that it must be irrational. Y'all, I thought that was really cool. I hope I didn't drag it out too much. Let me know what you think.